Excellent. Thanks very much. I'm all,
You got a label.
yeah, hands-free. Fantastic. Yeah, thanks everyone for coming along, and thanks for the invitation to come and speak. You know, as the introduction says, you know, my background was originally in the automotive industry for, you know, I don't know how many years, and so I felt myself conflicted around about the year 2000, the millennial year, and I decided that the sustainability light had to switch on, and then I moved over, and of course, as was just mentioned, that my work in mechanical engineering was a very natural segue into energy efficiency, and I found that when I went and studied Cert for Renewable Energy at Swinburne University, and it was not only a natural segue, but it was more interesting than what I was doing before. So that background led me to get involved in energy efficiency programs, and of course, essentially over the last probably 16 years, over 3 councils now, as was said, Hume, Darebin, and Moreland. My role is basically to identify carbon reduction measures for the organisation, for its corporate operations, which generally is its building portfolio, its public lighting, and fleet operations. And of course, one of the things we're going to focus on tonight is mainly the fleet operations, and that really has a sort of strong connection with me because of my background as a qualified diesel mechanic working in the industry years and years ago, and always wanting to actually clean up the act of the mobility sector. So what I thought I'd do tonight was I've been asked to sort of, you know, just briefly talk about a lot of the energy efficiency measures that I've been rolling out over those years, or this is in particular at Moreland, and then I'll put more focus on the hydrogen fuel cell project. I'm not going to talk in detail about the project itself because I explained before that we're sort of in a fairly delicate stage at the moment where we're doing planning, community consultation and design, and we really can't talk too much about it until we've gone through that process. You know, it's one of those unique situations where we're proposing to build a hydrogen refuelling station at the Council's Operations Centre, but of course the thing is we are also the planning authority, so we have to self-assess ourselves and be very open and transparent. So, but what I'll do is I'll talk about the technology that underpinned the reason why we decided to move in this direction for the heavy plant, having already done extensive work in introducing an EV culture into the council operations, and I'll talk about that as well. So what I'm going to do is I'm just going to put a whole bunch of photos up, and I'm going to talk to those photos very quickly, and if anything about those particular projects stimulates a question, then we'll workshop it later on, but we'll just flow through it fairly quickly. So what we're looking at here is secondary glazing retrofit. Now we've done a lot in that area, and that particular photo is the concert hall at the Coburg Civic Centre. And essentially what it is working on a lot of older and more historic buildings. There's a lot of historic windows in there, double hung windows, and so we needed to come up with solutions where we could actually insulate those windows. So we've done a lot of work in secondary glazing. What we've also done too is in 2 of our public pools, aquatic centres, the pool hall, they're a bit of a problem, those ones, because essentially you're maintaining about a high humidity 30-degree temperature on the inside, and it can be 2 degrees on the outside. And if you've got no insulation, you can imagine how much those windows rain. And so what we did was it was part of the federal government SEEP program many years ago, and we actually triple glazed those windows, and we came up with a solution where we could actually control the moisture between those 2 panes, and it works really well. And the feedback we were getting from people that used to sit with their back to those windows was no longer was their back cold, you know. And of course, the middle of winter you could see through the glass. It wasn't raining like it used to. There's a usual suspect. A lot of historic buildings. That's one of the most historic part of the Coburg Civic Centre, right above the executive building there, the old councillors' chambers. Terracotta roof, pitched roof. Had been retrofitted with an integrated air conditioning system many years ago, but of course it had no bulk insulation and no radiant barrier under those tiles, and so we did a lot of work to actually clean that up as well. Hot water retrofits. That was a unique one that we came up with a bit of a solution there, where we had heat pumps that were designed to be outside, but we had a special duct made up to vent the cold air outside the room so that it worked efficiently. And of course, we've done a lot of upgrades in sports change rooms and bits and pieces like that for the domestic hot water, and switch them over to heat pumps from electric resistive. Voltage power optimization transformers on our bigger buildings. Typically where we've installed those, you will see about a 7 or 8% reduction in electricity consumption overnight just by installing those, by And generally speaking, that particular one is the Coburg Civic Centre, is a couple of 200 kVA units that are servicing 95% of the site. And by literally tapping the grid voltage 6%, so the ebb and flow of the grid variables goes through that, but you're tapping at 6%, and that 6% reduction in voltage actually generates an 8% saving across the whole site. And when you think about electricity bills of $8,000 a month, that's quite significant. Of course, thermal pool covers in the aquatic centres, and that is one of the aquatic centres that I mentioned before, with those large windows there that are now triple glazed and very well insulated. Demonstrable savings as a result of actually putting thermal pool covers on those pool overnight, because you're maintaining a temperature of 30 degrees. And it also, it's an asset protection thing, because basically it's obviously very corrosive, humid air, and it can actually really destroy your building, more so than salt environments. And so it helps reduce that as well. So it's a bit of asset protection. That's not a very exciting photo, but basically that is a comprehensive building management system with a series of direct digital controllers that controls all of the building mechanical, some hydraulic, some lighting, and various different things. And what we do now as part of a policy with new buildings is we actually link the building management system to the security system, and essentially through a series of relays and contactors and main switchboards, which means basically that it's an easy way to control whether things are on when nobody's there. If nobody's there, then nothing needs to be on. So basically, once that security system is armed, the various different electronic components in here just shut down the things that don't need to be on. Solar PV and hot water. So we've done a lot of smaller solar systems, but about a couple of years ago we moved into the commercial space. We've pretty much maxed out the roof that we can in most of the council buildings now. So we've got about 660 kilowatts installed across council buildings. There's bits and pieces of more to be had. We've got what we call a solar on lease program. So we work with community groups that are lessees of a council building, but they pay the utilities. And the project we developed actually won a UN award last year, because essentially what it was doing was giving those community people access to solar, but they didn't have to actually come up with the capital to do it. So essentially what we do is we go and design, install and own and operate a solar PV system on a council-owned building where somebody else is paying the utilities. And the tenants then pay us back over 10 years, but only with the savings that have been achieved by the solar system, but 80% of them. So they get a 20% saving on their electricity bill straight up. And of course, once that's paid off, all the savings go to them and they won't be charged for any maintenance. So that's an 80 kilowatt system at the Coburg Leisure Centre. Of course, the commercial scale solar hot water at some of the aquatic centres, and of course the inverters that go with those large systems as well. Then we get into HVAC. We've done a lot of work on HVAC. Before solar became so cost competitive, and I remember years ago, and it was when I was at Darebin Council, and they asked me to do a paper on a microgeneration feasibility study, and that was back in the days when the general price of solar was around about $4.50, $5 a watt. And it's quite a bit different now. And of course, back in those days, it really wasn't financially viable. And so if you did it for aspirational reasons. But essentially it's changed all now. But the school of thought in those days was do all your energy efficiency, establish your base load, and then put an appropriately sized solar PV system on. The irony of that is that if people didn't want to do energy efficiency, the solar PV is probably the best bang for buck as far as energy efficiency is concerned. And obviously we're not promoting doing that. But what was the best bang for buck back in those days was the HVAC systems, because generally you would find, particularly in a commercial building, is that 60% of your load would have been heating, ventilation and air conditioning. So there's a series of examples that we've done there. We have, the council has an aspirational target to move away from fossil fuel for stationary energy. So pretty much the only place we use natural gas now, we pretty much all the new buildings we bring on stream now are all electric buildings, and it's mandated that 20% of the energy that is likely to be consumed by that building has to be produced with renewables on site. So it mandates a solar PV system as part of the build. But pretty much the only place we use natural gas now is to heat water in public pools. You can do it with heat pumps, and of course it's getting more competitive now, but back in the days when these high efficiency condensing boilers were put in, the heat pumps were about 3 times the cost of actually doing it. So we simply didn't have the capital to do it. So we did the next best thing, which has changed from a really old, inefficient gas boiler to a highly efficient condensing boiler that is around about 97% efficient. And it's amazing the savings that we achieve by simply transitioning from, say, a 20-year-old, let's give it the benefit of the doubt, 70% efficiency up to about 95%. And we were actually saving over 50% in our gas over a 12-month period just by transitioning to those and putting better control measures in as well. Typical package system incorporating all the economy options, the economy dampers, the variable speed fans, the variable speed compressors, all controlled by a sophisticated building management system and set up in accordance with the council's, what I developed for them about 7 years ago, was an indoor thermal comfort policy. So it's a blueprint to say this is what temperature and humidity that we will run our buildings, and it's all underpinned by obviously science and meeting work cover requirements. And so the control engineer set it up all that way. This is a very recent project here. This is at the Coburg Civic Centre. We've basically transitioned that entire civic precinct away from gas, apart from the town hall, which has got radiant heaters in it. But essentially the concert hall and all office areas are now serviced for heating, cooling and ventilation by very high efficiency reverse cycle air conditioners. And so we've got these big condensers up here. We ended up taking 1.2 megawatts of old inefficient gas boilers off the roof and replacing it with those two, which is a combined 320 kilowatts of high efficiency heat pump with coefficients of performance over 4 to 1. And they had to come from Europe to get that efficiency, because the European stuff with Eurovent rating is typically much higher than what it is here. And it's working very effectively. We had our doubters. A lot of the engineers in the industry said, "Well, it's not going to work. You can't heat a building, a commercial building, without gas. It just can't happen, But we've proved them wrong, and it's actually, the comfort levels are actually far superior than they were before because of the way that we did it. There was a lot of changes that we made in the hydraulic system downstream of those to actually improve the system, and it works very effectively. And then, of course, lighting upgrades. And so we've done a lot of work on lighting upgrades over the last 8 years. And, of course, in the early days, it was all moving to a more efficient electronic ballast fluorescent until the LEDs got to a level where they were not only reliable but very efficient. So we've done a lot of work upgrading the park lighting. And what we've done is actually brought a lot of our open space, which were unmetered distributor lighting, very, very poorly maintained and very poor efficiency levels, to a high efficiency LED, all operating in accordance with also a public lighting policy developed specifically for the council operations. That again is the pool that I showed before. We obviously did a lot of things there with the triple glazed windows, and we actually engineered some brackets up and actually put some high-end LEDs to service. It used to have these massive surface mounted 1 kilowatt HID lamps in the roof, and they were a bit of a shocker. And so we ended up actually improving the light levels and reducing the energy consumption by 55%. So it's been working very effectively. This one, of course, is an example of a street LED by Sylvania. So essentially we've done the complete bulk change of Moreland, which involved changing over 8,700 80-watt mercury vapours. Now, load table consumption for there is 96 watts, and they're on for 12 hours a night. These ones are actually a higher light level because they disperse the light on the ground where it's supposed to be and not diffused all over the place with very minimum upwards light spill ratio. Load table 21 watts. And so you can imagine the bang for buck for that as a retrofit was incredible. And we're talking over 3,500 tonnes of greenhouse gas reduction on the corporate footprint in a year. And something like $300,000 a year saving on electricity and operation and maintenance charges. And so it was a really good thing to do. This one is an example of what I refer to as the Holy Grail. I was at a conference in Brisbane about 5 or 6 years ago, and there was a guy that was saying every light source will be LEDs in 5 years' time. And I thought, I bailed him up after his session and just wanted to sort of clarify that. And he said, no, it'll happen. And sure enough, I said, the Holy Grail will be when there's an LED to replace a 2 kilowatt sports lighter, like at the MCG. That's it. They're called the Raptor. They're 1,260 watts, and they are way superior than the 2 kilowatt sports lighter. the really interesting thing there, and you probably would have noticed if you've been watching a bit of football in some of these new stadiums they've built, because they've actually used this technology in there, because the flexibility of LEDs, they can set up this disco lighting, you know, which you could never do with an HID, because they need warm up and warm down cycles, and very, very temperamental. So that's a reserve in Coburg where they've been fitted, and they're very effective. Cogeneration. This is not a good news story. I project managed the installation of this one. It's a 75 kilowatt reciprocating engine. It actually dragged me back to my roots when I worked as a mechanic many years ago, because essentially I found myself in the plant room when they were doing the first service on this engine. I felt like I was in some sort of parallel universe, because I thought to myself, you know, it's the 21st century and this guy's changing spark plugs on an internal combustion engine that spews all this stuff out the exhaust. I just didn't think it was right. But I was very skeptical about this technology, but I was given that job to project manage. Another person left, and I took it on. But essentially, when it got it up and running, they both ran very reliably. This is a 65 kilowatt gas turbine. And of course, the little blue gen over here, we installed one of those many years ago, and it worked quite effectively for a few years. But of course, when the heat exchanger failed, ceramic fuel cells had gone out of business, and so there was no way that we could keep it running. But Solid Power have actually taken it on now, and they're actually trying to revive the technology. CSIRO developed technology in the 80s, and very, very clever. But those two units at aquatic centres probably represent a $1.2 million investment. We switched them off 3 years ago. They are stranded assets. And the reason for that is they were working as per design, but they were costing us money to run. And this is something that we were misled basically by the industry that sort of pushes them. And this is way before gas prices went up. So essentially we're paying them off by leaving them switched off. I had a feasibility study on the site that this one, it was a leisure centre in Fawkner. And I basically said to the consultants after a couple of years of running that, I said, what I want you to do is look at this site and say, if I had $650,000 to spend and I wanted to get a 500 tonne greenhouse gas reduction from this site annually, what technology would I employ? Now, I had a preconceived notion what that would be, and it was a sigh of relief when they came back with their report, and it was exactly what I suggested. They said you would not install an internal combustion gas-fired cogeneration. You would install 200 kilowatts of PV and change your gas boilers to the highest efficiency condensing boilers, which we've actually done at this site now with this switched off. And then you would get a return on investment, which they would never give you, but you would also achieve those figures using 2,500 gigajoules less natural gas a year. And so that fit for the council, but not using fossil fuels and sort of switching into renewables. We haven't done the solar yet, that's yet to come. But very unfortunate that they are stranded assets, and it's just a reality. It's just the way it is. And of course, it would be even worse business case now because the price of natural gas has gone up so much. The Melbourne Renewable Energy Project, you've probably heard about this one. There's a little celebration we had at the Crowlands Hall a few months ago. And this is a photo of basically Challicum Hills. Now, what that is, it's a project that was, the project inception was the City of Melbourne. And when we were invited to become part of it, we said, yep, absolutely, that's going to fit with what we do. And I might just go back a little bit. Moreland are a NCOS accredited carbon neutral council since 2012. Now, when we did that, we actually received a little bit of criticism from local community groups because they said, oh, look, you know, you're just buying offsets and you're shirking your responsibilities elsewhere. And I found myself actually defending the council on a couple of occasions at public forums because essentially I said, look, you know, you would have a fair argument if the council had said, look, we're not going to give you any energy efficiency money anymore. We're going to spend it on offsets. But they didn't touch my budget, not one bit, because it wasn't what they were after. They wanted to continue to reduce that energy consumption, increase the efficiency. But go carbon neutral and then work back from that. So when this project came along, it was an opportunity for us to actually solve that problem. The criticism was that we were buying cheap international offsets, although accredited, and we weren't investing in local renewable energy. And so we took that on board. And this project was fit for the task, basically, because essentially what it was 14 organisations getting together and going to the market and saying, who's out there that's prepared to build a renewable energy generator that will provide our organisations, our corporate requirements, the power that we need. The total load all of those. I mean, Moreland and a couple of the other members have got their entire corporate electricity requirements into this project. So every electron that we buy from January next year will be coming from the Crowlands wind farm, an 80 megawatt wind farm that will be built in just 25 k's northeast of Ararat, not very far from Challacombe Hills wind farm. And it will be built specifically for this group. So it is the true power purchasing agreement where you're basically bypassing the system and then going directly to the generator and having a deal. And so the deal is with Pacific Hydro and Tango Energy, which is their retail arm. And they will be providing all of council's electricity so that we can actually guarantee that we are investing in local renewable energy and we're maintaining that carbon neutrality at the same time. I was a part of the design and also the evaluation committee of this project, and it was it had its ups and downs, and it was over a 3-year period, but we got it done in the end, and it's really exciting. And I can tell that it's become a blueprint for a lot of other organisations, universities and other corporations that actually want to use this, because one of the things City of Melbourne did, and it's available on their website if anybody wants to download it, it's basically a blueprint on how we went about this power purchasing agreement and the success that it achieved. And then, of course, electric vehicles, and back to my roots. And so we got involved in the Victorian Government's electric vehicle trial back in 2012, and we had one of their Nissan Leafs for about 6 months. It was a really successful trial. In fact, the vehicle that we had, I think holds the record as the largest mileage vehicle for that 6-month period, because essentially what we were doing, we wanted a true assessment of what this would be like in our fleet. So, and then, of course, while we did that, we put in a business case to the Victorian Government to actually fund the first electric vehicle fast charging station in Victoria, which is at Coburg Civic Centre and still operating this day. Immediately after we finished the trial, we bought our first vehicle, which is this one. We logoed it all up to celebrate. And then, of course, we're on a journey now to transition our passenger fleet to zero emissions vehicles. And only 2 weeks ago have adopted a new fleet policy that basically talks about zero emissions first. And it also mandates if the fallback option has to be a vehicle with an internal combustion engine, that it's got to meet stringent emission standards. And those emission standards are 100 grams of CO2 combined per kilometre, which would be one of the toughest in Australia. And just to give you an example, a hybrid Camry and a hybrid Prius station wagon do not meet that policy. And so it essentially means that you couldn't actually have a vehicle unless it's got some form of electric drivetrain in the fleet. And that is a blueprint on a path to zero emissions eventually. And obviously that's why we want to sort of go for zero emissions. And that's where the hydrogen kicks in later on. We actually had an electric vehicle feasibility study that then underpinned moving in this direction back in 2014. And that is a public document. It can be downloaded off the council's website if anybody's interested. And we own and operate a network of 11 EV charging stations across the municipality. We're literally installing another one at Coburg Civic Centre this week, another 2 out in Oak Park probably in the next 6 months, and continuing to find opportunities to put destination fast charge stations as we now see ourselves in the realm of the next generation of electric vehicles that have bigger batteries, faster charging. So no longer is it sit in a car park and trickle charge. It's basically get out of town and find an opportunity to get a quick spurt, a zap and go as we call it. And so that's what we're looking at now, looking at opportunities to put destination charging stations in. Okay, now the core one is hydrogen as a fleet fuel. So basically the reason that I recommend that we go down this road, and again, it was my background, is that, and I might just say to begin with, is that, and I was talking to somebody just before the presentation, that I've been working on this about 3 years now, and I've been thinking about hydrogen for probably 10 years. In fact, I was lucky enough to actually have a ride on one of the hydrogen fuel cell buses in Perth 10 years ago. I've seen it for a long time as the viable option for heavy vehicles over battery technology, but that doesn't mean that I have a preference for one or the other. And what I was saying before is there's this building momentum that I'm seeing in the networks, where you've got your battery electric vehicle fraternity and you've got your hydrogen fuel cell fraternity, and they're arguing with each other. Mine's better than yours, sort of thing, you know. And I said, look, there is no argument. I'm 110% behind both technologies. and powered by renewable energy, they are the way to go. We must electrify mobility and we must power our mobility with renewable energy, but there's several paths you can take once you've done that. And it doesn't matter if each other want to play in each other's space. I said to a group of people who were having an argument at a presentation, I said, look, you know, you're arguing about something that's irrelevant. The guy over there, the fossil fuel guy, is laughing at you. You're just tearing yourself apart, you know, and it's not worth it. It's basically about the right technology for the right purpose. And that's one of the reasons why we've chosen to go with hydrogen fuel cell in the heavy vehicle space, and I'll go into the reasons why in the presentation. Now, this basically was extracted from a presentation I did at the Eco Cities Congress last year, and they are the primary reasons that underpin the reason we're moving in this direction. We need to understand the urgent need to reduce emissions from fleet operations, and of course, particularly heavy fleet. Now, where that's relevant, the Moreland Council, and most councils would be the same, have waste collection. And we turn over probably 600 kilolitres of diesel a year for council operations. That's actually come down a couple of hundred kilolitres over the last few years by incorporating efficiencies. Of the 300 vehicles that we have diesel vehicles we have in our fleet, only 17 of them use 60% of that fuel, and that's waste collection. You talk about, you know, fuel economy that's really good of 5 litres per 100 kilometres. Try 120 litres per 100 kilometres, and then you're talking in a different space. The second one, of course, and again, that comes back to my roots as a mechanic, recognise the inefficiencies associated with continued use of internal combustion engines. They met a purpose 100 years ago, but they really are a shocking idea. You know, the idea that you compress a fine carbon, ignite it, it goes bang, and all this crap comes out the back, and that's the way we choose to go from point A to point B in the 21st century. It can be done better, and that's the reason we need to move to electric drivetrains. And then, of course, that speaks for itself. Again, moving renewable energy into the fleet fuel space, and that's the best way to do it. And this is the one where the argument comes up quite a lot, acknowledging power to weight ratio and refueling time limitations of battery technology for commercial vehicles. And as I said before, there's people out there making electric trucks, electric buses, that's fine. Again, every internal combustion, fossil fuel burning vehicle that they displace is a good thing. And if they want to do that, that's fine. Everybody's got their different ideas, but they can coexist. And this is a big one for us. We've got a curfew on our operations centre at the moment because people complain about those 17 trucks starting up, idling for 10 minutes before they go out and do their business. So we know that they can lift off straight away and they're 70% quieter. So how does it all work? Green hydrogen is what we're talking about. We're not talking about hydrogen made from fossil fuels by steam reformation or any other method. We're talking about green hydrogen. So basically what we'll do is we'll harvest stormwater. We're planning to put about a 1.2 megawatt solar system on site and also have a grid connection agreement with a wind farm operator that's got a large portfolio so that we can run the electrolyzers overnight and keep making hydrogen, you know, as long as you've got the water. Just to give you some basic figures, it varies a little bit, but generally speaking, when you electrolyse water, you need about 11 litres of water and about 35 to 45 kilowatt hours of electricity to make 1 kilogram of hydrogen. Now, 1 kilogram of hydrogen has an energy content of around about 33 kilowatt hours. And then if you use that hydrogen through a fuel cell and accept the losses through the fuel cell, you end up with around about 23 kilowatt hours of usable energy at the wheels. And that's where the power to weight ratio comes in before, because you're talking about 23 kilowatt hours in a kilogram of hydrogen versus, let's give the batteries a benefit of the doubt, say 300 watt hours per kilogram. And that really is the difference. And so it comes back to what I said before, horses for courses. So once you've done that, you've created your hydrogen, you in future put it into a hydrogen fuel cell vehicle, and then you're completing that, that picture. Now, I put this in here. I've got a little bit of a cheat sheet here because I'm not a chemical engineer and I cannot explain how that works. So what I'll do is I'll read as you look at this graphic. So hydrogen gas is channeled through plates to the anode on one side of the fuel cell, whilst oxygen from the surrounding air is channeled through the cathode on the other side of the fuel cell. A catalyst causes the hydrogen to split into positive protons and negative electrons. And this process creates electrical current, which of course is used to power an electric motor or charge a battery. And the only byproducts of the process are water and heat and a little bit of oxygen. So this technology is not new, but it's been developed and refined over the years, and the proton exchange membrane fuel cells, which appear to be the particular fuel cell of choice for the vehicle manufacturers, are really achieving sort of great longevity and high efficiency. They're running between 55% and 60% efficient these days. The same as battery density is getting better. You know, the efficiency of fuel cells has gone up about 10% over the last probably 6 or 7 years. And so it's constant development, supply and demand. And so that's basically how it works. Now this is the question again that comes up in this debate, you know, why hydrogen and not batteries? And again, I said there is no debate here. They both coexist and they have their different things. But what I thought I'd do is I'd put this in. Now, this is a bit dated, this table, and I'll just explain what it is. It was done by a university in the United States, but it's probably, I don't know, 7 or 8 years old now. So as you can see, it's assuming efficiencies quite low by modern standards for the fuel cells and also for the batteries. But essentially what they were wanting to do, and why I'm sort of showing this, is that it is probably the main reason why we're choosing to go hydrogen fuel cell with our waste vehicles over batteries. So you're talking the same energy input, you're going through all your various different sort of flows through to the drivetrain, and that vehicle's got to be able to achieve 300 miles. But this is the one that really stands out when you look at these two. To do all that, the battery electric vehicle weighs 2,200 kilograms, but the fuel cell vehicle weighs 1,200 kilograms. Now, they've changed a little bit. But typically what you'll find is if you want to replicate the duty cycle of a conventional vehicle with an internal combustion engine, and so assume that it can go the same distance and can do all the same things, then you're using batteries to do that, you're going to be looking at somewhere between 30 and 40% heavier. You know, it's no secret that a Tesla Model S weighs 2.5 tons, and a lot of that is the battery. And say, for instance, the Toyota Mirai, it's a slightly smaller vehicle, and it actually does have a heavy battery in it. They've used the Toyota's nickel metal hydride battery in it, and it weighs about 1,800 kilograms, but it can go the same distance. So we're not talking about specifically with the vehicles, but that is probably the key reason why we're choosing to use it in the waste vehicles. And the reason for that is that our waste vehicles are 6x4, what they call 6x4 compactors, with a gross vehicle mass of 23 tonnes. Now, they are on the limit, the road limit, every day. In fact, they have to stop picking up bins because the onboard weight sensor says not one more bin because you're overloaded, and you could get fined. So what we needed to do is we need to transition to an electric drivetrain and renewable energy. And we've already run the numbers on this through the engineers. And we know that if we removed all of the internal combustion engine components that we don't need to convert that vehicle, the same body, to an electric drivetrain, we'd have 2,100 kilograms of materials that we would remove. With the fuel cell powertrain, to match the 280 litres of diesel, so in other words, be able to do exactly what the 280 litres of diesel does and go the same distance, it's around about 1,800 kilograms. But if we then removed all the internal combustion engine gear and put a battery electric vehicle drivetrain to do the same as that 280 litres of diesel, we need to add 3,600 kilograms. So we would increase the tare weight of the vehicle by 1.5 tonnes to be able to do the same as what the diesel does. Now that equates to 1,500 less bins that truck can pick up a day. And if you need all of those trucks to do your rounds every day and every week, you'd have to increase the size of your fleet by 40%. And so that's probably the main reason why we're choosing to go to the hydrogen fuel cell. There's basically the anatomy. This is courtesy Honda with one of the early Clarities. And so basically you've got your high pressure tank, you've got your fuel cell stack that generates the electricity, you've got your buffer battery, and essentially what that's there to do is to capture the energy from regeneration in the braking, typically what a battery electric vehicle does now, or a hybrid vehicle. But it also assists in acceleration. The modern fuel cells now are actually very reactive, but essentially it's basically from 0 to 100% output, there's a 2-second delay. And so that battery there is to fill that gap. Now, I've driven a hydrogen fuel cell vehicle, and you wouldn't know that you're driving a hydrogen fuel cell vehicle. You would think it's just a battery electric vehicle. The response is exactly the same as anybody that has driven a electric vehicle. And so the way they've worked it in is very very good. You know, this again speaks for itself, and the sizes of those components are relative to what they would be. So the power of that and the power of that are equivalent, so you can look at the differences between the two. Very inefficient way to create mobility and lots of waste. And of course, there are upstream and downstream impacts on the environment by using these things. Whereas if you use these things and you use renewable energy, you're covering off on those upstream and downstream impacts. And so that's the key to it. And of course, when you're using this, you don't need all the gear that bolts onto the back of this to actually get it to the wheels and get it to do it efficiently. So this is the main reasons that we set up the moving to the hydrogen fuel cell or the electric drivetrain. And basically, the top one and the bottom one are the same as if you were going battery electric, but the other ones are the key reasons. Weight. Vehicle tear weight can be matched or reduced using fuel cell electric vehicle technology, which gives you improved payload advantages. And see, this is the point that I make often when they have these arguments over it. It really doesn't matter that the Tesla weighs 2.5 tonnes. The electric motor doesn't care. It's got so much torque, you wouldn't even know it. But when you've got payload, everything matters, because that's basically what it's there to do, to keep the tear weight of the vehicle down so you can increase your payload and then get more efficiency out of the vehicle. Range. Hydrogen fuel cell vehicles typically have an equivalent range to an internal combustion engine without payload compromises. Refueling. Again, we're talking, and this is something that scares people when you start to talk about the pressures in these hydrogen tanks, but I'll talk about that a little bit. But the Type 4 tanks they're using now, 700 bar, which is 10,000 psi. And the reason for that is that hydrogen is energy dense, but you need to compress it to get it in a small space to get that density. And of course, if you haven't got a lot of space for tanks, then you need to compress it to a high pressure. Generally, the hydrogen fuel cell buses you see overseas have got 350 bar tanks, so it's a lower pressure, but there's more tanks and more area of tanks because they've got all that roof to fill up with tanks, and so they don't need to run the higher pressure. And they can run a higher flow to fill them up quicker because they generally have about twice the amount of hydrogen that a waste collection vehicle would use, so it can do its daily cycle. But having said that, and using again the Toyota Mirai or the Hyundai that's just come out as an example, they've got 5 or 6 kilograms of hydrogen on board, which equates to around about, say, 130 kilowatt hours of electricity. And they can be refueled in between 3 to 5 minutes just with 700 bar. And the refueling is very simple. One of the things that's really good, which is an absolute pain with the electric vehicle industry, is the world couldn't get together and decide on what footprint they wanted for the charging nozzle. And so everybody's got to run around with a boot full of adapters to know where they're going to fill up. But hydrogen's different. It's the same nipple or nozzle for hydrogen, whether it's a Class 8 truck or a small vehicle. It's exactly the same. And so there's no disparity differences when you're going to refuel, and that's important when we start building up a network of outlets where you can actually refuel vehicles. And then of course the other things there. So when we went to a global heavy vehicle manufacturer to actually say, will you build us prototype vehicles, we went to them with design criteria, because what we were going to do, we weren't going to say, look, can you build a truck just for us to do what we want to do? We were going to say to them, we want you to build a truck that'll suit us, but it'll suit any other customer that you sell that diesel derivative to. And so to do that, it needed to be able to do everything that the diesel version does now. And so we set up these basic vehicle design criteria to make sure that the project is a success. And I might just qualify that, I've been involved over the years with different retrofit projects for electric vehicles or zero emissions vehicles. And I've read a lot about some of the projects, and what you find often is that if you want to bring the masses on board and say this is the way we need to do it, they fear change. And if you say, look, here's a battery electric vehicle, but we haven't given you a fuel gauge, we've given you this little battery meter, and so it's a little amp meter. So and you need to read a book to know how to use it. They'll just glaze over. I've seen it happen, and so, taking all those experiences on board, what I've said to the global vehicle manufacturer is that I actually said to them, I was in a government office in Spring Street when we were talking about funding with the state government, I said, this truck has to be the Tesla Model S of trucks. Now, the reason that car is successful is because they're not building an electric car, they're building a really cool car that people will want. It just has a different drivetrain and uses different fuel. We've got to make this the same. And I can tell you from working in the heavy vehicle industry that the fleet managers and trucking operators are even more fickle about that sort of thing than the average punter with a car. They want to know there's no inconvenience. So we said we don't want any increase in tare weight. We want superior torque and power delivery. Well, that's a no-brainer when you're moving from a diesel engine drivetrain to an electric motor, particularly a permanent magnet, really high efficiency motor. At least equal or prefer better operational range than what the diesel's doing now. And so the minimum is it's got to be able to do what the diesel can do. Otherwise, you won't capture them. You need to capture them. Improved drivability. Again, it's a no-brainer because essentially what you're doing is you're taking out all of that heavy vehicle drivetrain, 6-speed automatic transmissions with all the bits and pieces that go with it that are not like the typical automatic transmission in your normal vehicle. They're very clunky. And when you move, in fact, it was one of the things when I presented this to council a couple of years ago, and one of the councillors says, so this truck will drive just like my Nissan Leaf. And I said, absolutely. Set up properly, it'll just drive like a Nissan Leaf, like an electric car. So it's all about how it's sort of set up. This was another important one. And this is to get, again, because of the industry we're talking about, the bodybuilders will glaze over. You say, look, you've got to change the design of your compactor body so that we can fit it onto one of these vehicles because we've got all our tanks and bits and pieces into place. Fuel cell electric vehicle conversion components not to penetrate traditional chassis area. And essentially what we were saying is that you come with a cab chassis that's got a fuel cell electric vehicle drivetrain. We've got to be able to take the compactor body off one of the diesels and put it straight on that, and it's got to fit. And that was the other one as well. And then, of course, zero emissions, powered only by renewable energy. You're really only transferring the problem elsewhere if you're not doing it that way. And ultimately, no compromise. And so that's what we went to them with, and they were very encouraged to hear that. This is an example of the sort of setup that you would see for a commercial scale hydrogen refueling station. So you've got your solar system on all your hard stand areas there, feeding into proton exchange membrane electrolyzers. And in this case, you've got 1.5 megawatts of electrolyzers. You've got the compressors to compress it. You've got buffer tanks where your low pressure is stored. You've got constant pressure tubes, and then you've got your cascade storage. Now the cascade storage, that's got some scary numbers up there. That's got 15,000 PSI in those constant pressure tubes. And the reason for that is that, and another reason why you're starting to see hydrogen being talked about a lot for large-scale energy storage. You know, we've got the Tesla battery in South Australia. Well, you can store a lot more energy in a much smaller footprint if you're storing it in hydrogen. But the important thing, and this is what the technical people say, is that it basically will store forever. It doesn't degrade. And so, you know, like a battery will trickle down over time. Every battery technology does. So you're not short cycling the compressors all the time. This constant pressure tube, so you've got your fuel bowsers. So you walk up your fuel bowser, you plug it in, and then you fill up your tank. Essentially, the compressors don't need to run because you've got a high pressure tank that's just equalizing with a lower pressure tank. And it's doing it very quickly. And as I said before, and we're talking, say, with the waste vehicles in the numbers that we've run, about 22 kilograms of hydrogen to match the 280 litres of diesel. There's a really complicated formula to work out the energy component and then the efficiencies and inefficiencies of the two different drivetrains. But essentially, those 22 kilograms of hydrogen will match the 280 litres of diesel, and that'll probably refuel in about 10 minutes, which is not that far removed from what it would cost, what it would take to actually refuel your 300-litre diesel tank. Now, this old chestnut, is hydrogen unsafe? This doesn't come up a lot for me when I'm in technical forums, but when it's a room full of average punters, all they want to talk about is the Hindenburg. Now, there's a couple of things here, and I put this in there because the title of this article from a study that was done in the US years and years ago is just gold. Don't paint your airship with rocket fuel, because in the 1990s, an ex-NASA scientist actually, it was his life's work after he retired from NASA was to actually find out exactly what happened in that accident. And what he actually was able to conclude, which was then confirmed by the Zeppelin company that built the Hindenburg, which is still operating today, making airships in Germany, that static electricity started fire on the fabric dope-covered skin with the rocket fuel on it. And incredibly, they were able to establish from the black and white footage from that accident in 1937 that no hydrogen was burning until 10 minutes after the fire started. And obviously, once it was all engulfed, the hydrogen is going to burn. The interesting thing also is because hydrogen is 14 times lighter than air, which is why they use it for airships. In fact, it's double the lightness of the helium, which they use because it's safe. Helium's only 7 times lighter and it's more expensive, and this is one of the reasons why they did it. But interestingly enough, when it burns, it just burns quickly up, so fast that you almost don't even feel the radiant heat coming from it. And one of the things they found was that it was a tragic accident, but the majority of people that died because they jumped off before it actually hit the ground, not because they were burned. And that was because once the hydrogen went, it sort of sucks the heat away because it goes up so high. This is an interesting test this university did, because they were wanting to establish once and for all, is hydrogen more dangerous than what we know or not? So what they fitted up a donor vehicle with I think it was a 700 bar hydrogen fuel tank in the back, and they set it up with an explosive device on the valve. And so they were setting up a catastrophic failure. And then they were going to test the car in both circumstances. What's the flammability of the existing vehicle with unleaded fuel? So it's just a conventional car, and they put the hydrogen tank in the back. The interesting thing was they actually knew that they had to conduct the hydrogen test first, because conducting the unleaded test would destroy the car and they'd have nothing to test. So as you can see what's happening, and they've enhanced this because hydrogen when it burns is virtually colourless, but you've got about a 20, 25 metre flame coming up once that explosive charge went off, and because it's under such high pressure, it self-ignites when it lets go. But as you can see, it goes up, blew the boot lid off, and after about 3 minutes it was down to about this. But there's and all they did was got under the car, cut the fuel line and gave it an ignition source. And that was the car after 3 minutes, which is why they did the hydrogen test first. So various different studies and universities in the US have concluded that hydrogen's no more or less dangerous than any other flammable substance. It's just different, and you just treat it differently. What I can say is that if anything good could have come out of that accident, what it did do, because the world thinks that hydrogen is unsafe because of what it did to the Hindenburg, the ISO standards for hydrogen storage, transport and use in a vehicle are probably 4 times greater than they need to be to alleviate people's concerns that there's a safety issue. So I came back to those tanks before. You see some of the testing has been done on these Type 4 tanks that have got 700 bar, 10,000 pounds in them. They're carbon fibre, and there's 3 different layers. Hydrogen has the effect on metal where it makes it, they call it embrittlement. And so if hydrogen's exposed to metal, it makes it brittle. So you've got a metal liner, then you've got a polyethylene liner, which isn't affected by hydrogen because it's non-toxic. It's really interesting when you look at it, an MSDS, like a safety data sheet for different types of substances. If you look at MSDS for diesel fuel, for instance, or unleaded petrol, there's about 5 or 6 red flags, toxic, carcinogenic, blah, blah, blah. MSDS for hydrogen, flammable. That's it. Non-toxic, it's not poison, and as we probably know, it's the most abundant element on the earth. So, as I said, the safety that's gone into these manufacturers and the tanks that they're using is incredible. In actual fact, in the testing that they did on a particular tank, they tried everything. They put it in a car and they crushed the car between 2 prime movers at 60 kilometres an hour so that the only thing left was the tank and it didn't breach. They did all those sort of tests. The only thing that did it, they fired a 50 calibre armour-piercing round at it twice in the same spot. That was the only thing that let it go. And so, the interesting thing is that it's the same material they use to make these tanks is what they line the fuel tanks of military aircraft with so that the bullets can't penetrate the fuel tank. And so it sort of goes with the territory, Now this is a little thing. That's me, and why you might think it's strange I'm underneath the car. That's a Toyota Mirai. Now, one of the things we talked about before, hydrogen, one of the byproducts of putting hydrogen through a fuel cell is that when those protons and electrons actually meet up with each other on the other side of the cathode, they turn back into H2O. And so they produce a lot of water. And the amount of moisture they produce is directly proportional to how much hydrogen you're pushing through the fuel cell. So what Toyota have done is very clever. It's actually got a little condensate tank underneath the car. And so the condensation from the fuel cell accumulates in this tank. And of course, as you're driving along the freeway, it just vents out of the back of the car. But there's a little button on the dash that says H2O. And the reason they've done that is that so you don't end up with a big pool of water on the garage floor or on the driveway, you press that button before you, as you're driving down the road, before you enter, and it just vents it from this tank. Now, what's coming out of that vent is 75 degree, 99.9% pure water. So I needed to demonstrate that, and people get really sheepish about it because they think, well, you're just putting a cup under an exhaust pipe, and you think of the condensate that comes out of an exhaust pipe that's full of toxic chemicals because it's coming from a carbon-based fuel. And so I needed to demonstrate this to show that, and there's a tea bag in that. There is a tea bag in that. And I'm alive today. No problem. Drinking cold tea. Well, it was actually hot tea. It was generally 75 degree water. Now, I put this in here because when we're talking about mobility and you know, fossil fuels and emissions, and it's on everybody's lips these days. And a couple of statements that I've used in various different presentations that are really important to sort of focus on. The top one, in actual fact, I met the author of the report that I plagiarised to grab this paragraph out in a conference up in Sydney about 3 years ago. And basically, he was the guy that was asked by the West Australian government to actually write a business case on the feasibility of running those hydrogen fuel cell buses in Perth. And what he was at pains to point out to the government was that you're asking me to compare a $1.2 million prototype with a $680,000 standard diesel, but you're not asking me to incorporate the upstream and downstream impacts of running those vehicles. And so that pretty much sums it up, because if you don't impose a cost on fossil fuels to reflect damages arising from their combustion, you are effectively applying a subsidy. And if you're doing that, you'll end up with an inefficient use of resources. And this is one of the reasons why we need things like carbon taxes, because they, you know, the polluter must pay. And as I say, it's an irrefutable concept. And this is the other scary piece of information. It's been confirmed over in Europe as well. Yeah, exactly. Don't say carbon tax, you know. Now, a lot of people probably, it scares people when you say this, but the Clean Air and Urban Landscapes Hub, operating out of Melbourne University, published a report in 2015, and they had been able to definitively prove that more people in 2015 died as a direct result of vehicle emissions than the road toll. We don't hear about that on the news. We hear about the road toll. And coincidentally, just recently, earlier this year, the European Union published a report, and they were able to determine, I'm not sure it was Europe or globally, but they said they were able to determine that 38,000 people had died as a direct result of diesel vehicles that didn't meet their emission standards, which was the whole VW emissions scandal thing. And it's because of the nitrous oxides, which is one of the reasons why there's now a big push away from diesels in Europe. And this is one of the reasons why when we talk to global vehicle manufacturers that are generally coming out of Europe or North America, they're very interested in talking about hydrogen because they actually see it as a viable alternative as a fuel, and then the electric traction motor for the mobility to the diesel, meeting the standards, because what they're watching is major cities around the world saying, well, you won't be able to operate a diesel within our city limits by 2025. And so they've got 7 years to come up with an alternative plan. And so that's why they're starting now. And that's it for me. So let's open it up. And so any question about any of the slides?
Yeah, with the waste trucks, are you doing energy recovery as well, like hydraulic accumulators or something like that? Because they do a lot of stop-start.
Well, no, not hydraulic, through the motor itself. Yeah, so you're just reversing the motor, and like we do in electric vehicles.
So you've got some of that there already.
Yeah. So what we're looking at is two 60 kilowatt fuel cells where the engine bay is, and then around a buffer battery where the transmission would normally go of around about, say, 45 kilowatt hours. And then you've got your traction motor, which is 160 kilowatts and capable of 2,500 Newton meters at 350 amps. The interesting thing about that, one of the projects was being done in North America, where they were doing this on a Class 8 truck. They found out the hard way how much torque an electric motor has, because they were braking axles. And so they had to actually write some new algorithms in the firmware. So when the guy put his foot on the accelerator, the computer was controlling what went to the motor, not the guy with his foot.
Thanks, Stuart. Thanks, Stuart. Really exciting. So many questions, I can't even remember them all, but some of your early stuff where you're giving examples of what you've done on buildings and the lighting and stuff, quite apart from the environmental benefits, are you able to reel off any payback periods?
Yeah.
And the other one, another one was just on the swimming pool, where you said you managed to stop the condensation between the windows with some sort of venting. I'd be really interested in hearing how you did that.
First question, when I started at Moreland in 2010, we established a blueprint that basically said we're looking for low-hanging fruit, and what we found was that blueprint would be within a 15-year return on investment. Because we found if we rolled it back any tighter than that, you would be missing some really important things. It's one of the really interesting questions that comes up when you're talking about a cache of energy efficiency measures that you can do. And say, for instance, you've got your you've gone out and identified your low-hanging fruit. But then, say, for instance, you know your HVAC stuff was around about sort of an 8 to 11-year return on investment. But then you might look at an individual, say, for instance, if you've got a meeting room off a public entry foyer that's got a light in it, and there's no way that it'll turn off. It hasn't got a PIR sensor. Now, actually getting an electrician to install a PIR sensor to control that one light, there is no business case. But you don't not do it because it's not a good look. So what we set out to do was to choose a range of projects for a 12-month budget period where you had an average, you met an average under 15-year return on investment. So you captured those just because you're demonstrating leadership, and little things like that can hurt a lot for the sake of actually just spending a few $100s, but never see a return on investment, you know what I mean? Second part of the question was there was no venting between that glass. What it is, and it was an interesting one actually, because it was a public tender, and so we invited everybody that did any kind of secondary glazing to submit a proposal. But one of the criteria in the specification was management of moisture between the two panes of glass. And a lot of them withdrew because they said, we can't guarantee that. But the people we gave the project to said, absolutely, we can guarantee it. And essentially the way they did it was, instead of actually putting a one-pane retrofit, you know, similar to an EcoMaster or a magnetite, they actually put an entire UPVC framed double glazing sealed unit in the reveal of the window. So it's like a typical aluminium commercial window where you've got a reveal of around about 75 mil. And their particular frame fit perfectly in that 75 mil. And so it was flush with the frame on the outside, and it was on the outside it was done. And so you were effectively sealing the cavity. You were putting in a thermally broken frame, which the aluminium wasn't, and you're also putting in an argon-filled sealed double glazing unit. So it was kind of going overboard, but that's what it needed to fix the task. And I'll tell you, the first morning after that was retrofitted, and it was 2 degrees overnight, that was the first place I went in the morning to see if there was any moisture between those panes, and it was the window was crystal clear. And the interesting thing is that both the centres are run by the YMCA. And they said it was a new perspective because in the winter they could see out the windows. They could see the football oval. They could see people in the park because they could never see because the windows were raining with that temperature diurnal between those two surfaces, you know. So, and then of course that was a graphic representation of the fact how well the window was insulated, because if it wasn't, it would be wet. So yeah, it was actually sealed, so there was no venting. There's venting within the actual new unit itself on the outside, but not between that unit and the original pane of glass. Yep.
A couple of things that were holding the hardship back were, first of all, the technology of the tanks.
Yep.
And the last I heard was the technology would have to advance in the production of laminates.
Yep.
And it appears that this has just about happened.
It has happened.
Has it introduced a cost and a technology in
Not yet.
this? Sorry?
Not yet, no. They're very expensive to make.
Yeah.
But it's like anything else. It's about supply and demand. I mean, they needed to, as you rightly pointed out, we're up to type 4 tanks now. So the type 1s, 2s and 3s that didn't involve a laminate or a carbon fibre, they were restricted to 350 bar. And the only way you could go 700 bar was to go for this type 4 tank, which is carbon fibre. And it's not just carbon fibre, it's woven in a certain way. If you see the machine that does it, it weaves the carbon fibre in a different way to any other form of manufacturing carbon fibre to give it that cross-sectional strength. But yeah, absolutely right. They're very expensive, and that's one of the reasons why the early derivatives of hydrogen fuel cell vehicles are expensive. But it's like anything else, you know, it's supply and demand. I mean, I remember I was at a conference years ago and somebody said that where electric cars are now is where mobile phones were with the Motorola brick. And we saw what happened with supply and demand. And so obviously as it gets more popular, the production techniques get more efficient and then the materials become cheaper and so on and so on. Right. But yeah, you're right. The technology's there. I mean, companies like Honda, Hyundai, Toyota, now Mercedes-Benz with their G-Class, those companies wouldn't put those tanks in those cars if they thought there was any risk. But the cost is the barrier at the moment, for sure.
The other thing I want to ask about is the source of power. It seems that you'd need an enormous solar array.
Yeah.
A few years ago, they were talking about generating the hydrogen from splitting ammonia.
Yep.
For instance, you'd have a solar furnace, which at very high temperature accomplishes that. You've got your hydrogen on one hand and nitrogen on the other.
That's right.
Simply inject. Have there been any work that you know of? That's
absolutely. In actual fact, a project that was announced about 3 or 4 months ago by the South Australian government is basically making ammonia as a transportation method to sell renewable energy to other countries. So basically transport the ammonia and then split the hydrogen out of the ammonia when it gets to the country, because it's the best way to transport it. And so there's a big project in Port Augusta where they're going to be making a huge amount of ammonia from renewables to then transport overseas. For us, that's another way of actually, I mean, we don't need that. Essentially, one of the unique things about hydrogen, and this is one of the reasons why you're seeing some remote communities and even mining companies are actually starting to get into this now. And some of the bigger mines in Western Australia, if you go out there, you can just see an array of diesel generators as far as the eye can see. And you've got to have trucks constantly, coming from the main city, like 600-800 kilometres, delivering tanker loads of diesel fuel to keep them fed. Whereas with green hydrogen using electrolysis, it's possible to make the fuel on site and then it becomes your battery for your stationary power. And so that's what they're very interested in, because generally they've got those resources. They've got solar, they've got a water source, and they've got the capability of actually creating storage for that renewable energy in a different form, in a battery form, and that becomes their baseload power rather than relying on those diesel generators. And then the cost of that is actually very expensive, but then you've got to play that off against the cost of transporting all that diesel fuel in from the mainland. And so some of the bigger companies like Linde Gas, who is a part of the BOC group, and also Air Liquide, they've actually got plug and play infrastructure that can do this. They can basically bring all the components, interconnect it, put it on site, and off you go. And essentially, and the things I showed before, that was a representation of what we're looking with our project. So the electrolyzers, for instance, have got all the necessary components inside them, and they're just essentially just in a module or compartmental shipping container. You just drop it on the ground, you feed it a water supply and renewable energy, and it will spit hydrogen out the other side. So there's a lot of advancement in that technology now, and there's a lot of key players that are involved in it.
Great, thank you.
Yeah, a few years ago there was a bit of a push on about using hydrogen directly as a fuel in a nice engine. It seemed to petered out. What happened with that type of philosophy?
Well, and there still is. There's still people out there. I know BMW were doing that back in the 90s. I think they were doing that. And, you know, I'm not going to pass judgment on why they did that. I mean, essentially, you know, my position is the internal combustion engine, no matter what you feed it, is an inefficient way to convert your fuel source into kinetic energy because there's so much wastage downstream. And I think it was just, they were looking at that because it was an easy way to decarbonise the mobility situation you're talking about. I remember there was a video from a guy that was involved in a group, I forget what they're called now, in California, and they were asked why they went all the way to hydrogen fuel cell without stopping to look at things like that, or CNG and things like that. And his response was, you know, you still have to go to an enormous lot of trouble to actually, you know, create the hydrogen and then make the modifications to the engine and everything like that. And our philosophy is and to create lower emissions, but you've still got emissions. And his philosophy was, we're just going to go that little bit further and go to zero and be done with it. And that generally is the push you see from a lot of the manufacturers of hydrogen fuel cell vehicles, as opposed to a hydrogen-powered internal combustion engine, is there are still some emissions. They just want to go with zero emissions. And then, of course, because you're doing it that way, you're taking out that internal combustion engine that, if you're lucky, has got around about 30% efficiency, and putting in an electric drive unit that's got up to 95% efficiency. And so it's a double whammy, really.
And also the other thing about electric motors is the simplicity in terms of maintenance costs. You know, like I think the Tesla's only got 20 moving parts. And
that's right.
The standard car's got 3,000 or 4,000. So
that's right.
That's a big difference.
Yeah. And the more you have those moving parts, there's more to go wrong down the track when they get old, you know.
Thank you.
Being greedy, but no one else seems to need a question. In a single talk, I think you've turned me around on hydrogen. But one of the hesitations I always had was I'm reluctant to set up another entire distribution network that I saw it needing. Are you saying basically that won't happen, that the electricity will be the distribution network, or locally produced electricity, and that mostly it will be produced on site? Or do you still see, if we go the hydrogen way in a serious way, that we'll need a distribution network, whether it's tankers or pipes or what?
Predominantly it will be make it on site. And the reason for that is actually very hard to transport unless it's in ammonia form. So in gaseous form, you don't get much bang for buck. I mean, I was actually really surprised only a couple of months ago, and I was driving down Dandenong Road, and there was a BOC tanker, and it looked really weird because it had a lot of cylinders in a cage, and they're looking on the side, hydrogen, compressed hydrogen. But given the space of that semi-trailer by comparison with a liquid fuel, there's only about 10% of what you would normally carry in a liquid form. So it's more feasible to make it where you want to use it, and use the electricity network to generate it, and, you know, just ensure that you're actually using renewable energy. And of course you can use on-site solar. You've got, there's an organisation called Hydrogen Mobility Australia. They're very newly established, and they only started in, I think it was February this year. And they've got around about 11 founding members. And the interesting thing about that is that 4 of their founding members are big oil companies, because they see an opportunity here. And you naturally think, oh, their opportunity is, well, hydrogen's a byproduct of their refining process, and so they could basically sell it. But they actually want to get into the green hydrogen market. And so one of the other members, a company called ITM Power, has successfully delivered hydrogen refueling stations across Europe. And in such a way that you wouldn't even know. There's a Shell service station in Berlin that's got a hydrogen refueling bowser in the same aisle as the diesel bowser, and it looks the same. And everything that happens to actually feed it is happening out the back, and they're basically generating it on site, storing it and dispensing it on site, and just using, again, the water network, whether it be potable or harvested, you know, one or the other, and the electricity network to actually generate that fuel.
Does the water need to be very clean?
Absolutely. And in actual fact, it wouldn't really matter how clean you think you've got it before you put it in the electrolyzer. They've got so many scrubbers inside that thing and reverse osmosis, because it's got to be, and it sounds really funny to say this, but and I was talking to the guys at Cyro out in Monash, and they were talking about when they generate hydrogen in their laboratories, it's got to be low moisture hydrogen. And you think, well, okay, it's coming out of water, how can it not have moisture in it? But essentially, the refining process before it goes into the electrolyzer, if it's got more moisture molecules, you don't get as high a grade of hydrogen that comes out the other side. So in medical grade sort of stuff, they really do dry it. And again, don't ask me to explain it. I'm not a chemical engineer, but how do you dry water? Don't you have nothing when you dry water? Yeah.
How many manufacturers did you talk to for vehicles before you settled on something?
Only one. I won't say who that is because we haven't finalised a deal with them yet. But basically, the manufacturer that we approached was strategic because they are the manufacturer of the vehicles that 60% of the waste industry in Australia uses right now. And so, you know, when we embarked on this and went down this road, we said, we're not doing this for us. We're doing this as a blueprint for others to follow. You know, it's not just about us. Yes, we want to decarbonise. We want to make our fleet operation zero emissions. But it's about getting everybody else on board. And so really encouragingly, a lot of neighbouring councils, and in fact, I had a meeting only on Monday this week with somebody from the city of Brisbane that was down in Melbourne that wanted to talk about the project and actually what they can do. And of course, they've got a lot of waste vehicles being such a large council. So, and of course, they run the same type of vehicle. And so what we set about doing was talking to the people that basically put that compactor package together in Australia, and it's made in Australia, about transitioning that model to a hydrogen fuel cell vehicle because of the flow-on benefits to the rest of the industry. And it's not only other councils, it's the big waste management companies that have been talking to us about this as well. They've been inquiring because they're generally an Australian arm of a multinational operating out of Europe that have got very, very high environmental reporting requirements. And so it filters down through their organisation. So they've expressed a lot of interest in what we're doing here as well.
It might be best to put my question. It might be best to put my question last because I wanted to talk about the financial implications and aspects of it. So go on with the technical and come back to me.
Go with that one? Yep. Okay, fantastic. You're on.
Yeah, okay. I've been, I live in a council area where I think that they're not quite as progressive as your own council, Moreland. And so it's been going through my mind a couple of things, like, for instance, what would you charge them if you came to consult for them? That's one question we can get back to later on. And the other one was that in that list of organisations that funded the lot of the job that you're doing and so forth, National Australia Bank. And I'm wondering how I can address that issue, make it relevant to the banking inquiry at the moment, and also use the same information to go to the council and say, look, you know, I, as a council payer, think that you should consider this and implement such and such program. So that's the basis of my concern.
Yeah, yeah. Well, firstly, I can't speak on behalf of any other MREP member. What they do is up to them. But I take your point. The cost benefit, so we had a fairly comprehensive feasibility study conducted in 2016 that looked at all the pros and cons and everything like that. And remembering, of course, that Moreland is an organisation that aspires to sustainability as a core value and strategic objective. And so they are prepared, and the MREP project was a perfect example, you know. We are going to pay more for electricity because we're buying renewables directly from a generator. But we are going to pay way more for that, way less for that electricity than if we were just to go and buy accredited green power from a retailer, like a massive amount. And so it was acceptable given all of the parameters that we talked about before, in that, you know, we wanted to satisfy community concern that we're investing in local renewable energy and not just buying international offsets. But that comes at a cost, and quite often, you know, this is what you have to do. And so with this project, yes, a business case was necessary, But you know, if it was borderline, it didn't mean you abandon it, because you need a starting point to actually stimulate interest with other people. And the way I liken it, and this is just my personal opinion, is it's no different to an organisation, you know, having a budget for marketing and communications, and you're basically spending money that you might never get back to sell your brand, but it's important so that your brand is known and people are aware of it. But coming back to the business case stacked up, and the reason it did was because getting multiple players involved that formed part of a consortium, they had the power to be able to provide a discount to put the package together, because it's in their interest to make it work, get it on the ground and make it work, so it can stimulate interest and then stimulate an industry that then, 5 years down the track, they can actually start returning dividends from. And so one of the things that we're discussing as part of the project is, obviously the fuel cell vehicles are more expensive to buy, and essentially, like, a typical garbage truck for us now is around about $390,000. If you went and bought it ready to pick up bins, it's about $390,000. So we've estimated the fuel cell version initially would be something like $475,000. But through the consortium, we're negotiating an OEM discount for a period of time, and the numbers suggest that you'll achieve parity in 5 years' time. And the way we did that, we did a comprehensive study on how much it costs us to own and operate our garbage trucks now. And it's $4.51 per kilometre over 5 years to own and operate that. And it would be 10 cents a kilometre more for the hydrogen. So basically what they're doing is saying, we'll cover that 10 cents for 5 years because we feel that parity will be achieved. And so we went out, we set out to say, we know how much this is going to cost because it's new, and somebody's going to have to take a hit in the back pocket to start off with. But our target was to operate the fuel cell vehicles at no more than it currently costs us to operate the diesel vehicles. And that was a target that the consortium was prepared to accept. And then, of course, it all comes down to whether or not they can get that financed, and they believe they can, and then get financial close. And that's where it's all at the moment. And that's why I can't talk too much about it. But absolutely, yeah, I mean, we're not going in hell for leather and just not worrying about what it costs. That does matter. But the primary objective is to make those things zero emissions. That's the target. So everything that happens underneath it, that's the target we're heading for.
How much would you ask us to spend today with my council?
Free. Spread the message.
Okay, I think it would be better to be able to go to the council and say, look, I have negotiated or can negotiate with you.
Well, look, I mean,
$1,000 because they like to talk. I've been to a few meetings and they'll listen to you if there's money involved, but if it's for 3 years.
yeah, you know, I've had situations like that before. I remember years and years ago at Moreland, and I basically bit back of the envelope calculation to say it is cost effective for us to move to battery electric vehicles. But at the time, the executive needed to hear it from a professional consultant. And so we paid them $10,000 to tell them exactly what I told them for free. But whatever it takes, you know, to get it on the ground.
Okay.
Yes, you can. Can I have one afterwards as well?
I live in the CBD, right in the middle of Chinatown, and we get people. There's a group called Residents 3000. We get someone from council monthly to sort of tell us what's going on. One of the big problems is that with the garbage trucks, there's around about 20 companies involved. So we've got garbage trucks sort of whizzing around everywhere. They'd like to reduce this to 3 or 4. And I think your experience in this would be invaluable. Perhaps I can... any suggestions as to...
Well, you might be interested to know, and I won't mention any names, that one of the lead contractors that does garbage for the City of Melbourne, we're already in discussions with about this project.
Great.
So it's kind of happening anyway.
Good.
Because generally it's a fairly neat, close-knit niche industry, and they all talk to each other. And when there's a game-changing opportunity to get involved, that's one of the reasons why they've been contacting us, wanting to know more about the project. And so it's important for them that this project gets off the ground, because they want to see it work so that they can embrace it later on. So it's kind of happening anyway.
Yeah.
And because Moreland are part of the Northern Alliance for Greenhouse Action, which includes the City of Melbourne, we're always exchanging ideas on this sort of stuff anyway.
Maybe I can just ask one. Oh, did you want to ask a question? Okay. Yeah, just one question while I got the mic. I was wondering if you have to cater for winter in generating the power and store extra hydrogen for the winter months.
Well, that's kind of a how long's a piece of string question, that one, because essentially, and it comes back to when we did the early work on the infrastructure. That example of infrastructure I showed you is a fully blown infrastructure plug and play. But essentially, you don't need 1.5 megawatts of electrolyzers if you're only running 3 prototype trucks, which is the beginning of it. But what you can do is you can set it up to accept that additional infrastructure as a plug and play later on by doing that future-proofing the site initially. So essentially, that infrastructure you're looking at there can hold at any one time 550 kilograms of hydrogen. And when initially those waste vehicles are used, they're holding 22 kilograms of hydrogen, but we've sort of worked out based on their daily run that they'll probably only use 12 to 14 kilograms. You've got a lot in reserve. And so essentially what it is, and that's what those buffer tanks are for, so that you can actually, as they say in the classics, make hay while the sun shines. And so when you've got the renewable energy available and you've got a constant supply of harvested stormwater, you just run those electrolyzers and just keep making hydrogen if you've got space to store it. And that's one of the reasons why you would feed it solar power during the day and have a connection agreement with, say, a renewable energy generator that's got a lot of wind in its portfolio somewhere in Australia. And generally what they're happening, typically in South Australia, they've got power to burn, as they say, at night that the market doesn't want, because it's they'll obviously give it away. And so that's the sort of arrangement that you'll have. And so it's about storing for the rainy day sort of thing. But one interesting point when you talk about that's one of the advantages of hydrogen fuel cells over the battery electric vehicles, is that they're not subjected to temperature. And so, as you probably know, battery electric vehicles, their performance drops off in really cold weather, where fuel cells can operate at the same level in minus 20 degrees because of the nature of what they do and the fact that they're actually generating a bit of heat themselves. And it's one of the things they looked at in Europe when they were talking about small delivery vans, where they talked about the amount of energy that has to come out of the battery in a battery electric vehicle to heat the cabin. Whereas in a fuel cell, you do actually generate heat from the fuel cell. So virtually, and of course, those fuel cells are liquid cooled. And so you've got a cooling system similar to an internal combustion engine. So you're virtually running the same heater core as you would in an internal combustion engine. But instead of using heat that's been generated from 300 degrees, it's heat that's been generated at 75 degrees, which is exactly what you need to heat the cabin. And that saves you a lot of energy in the whole process. And so the hydrogen fuel cell vehicle, its performance doesn't degrade if in varying weather conditions. And that's another really important thing for commercial vehicle operators.
Yeah, I was just wondering about the cost of the electrolyzers, and is there any likelihood of them being rolled out very, very quickly? I ask this because I come from the Latrobe Valley, and of course the Japanese and AGL are very keen on producing hydrogen from coal. And my great wish is that we can see the hydrogen being produced from electrolysis really cheaply and very, very quickly everywhere.
I've got a really good story to tell you about that one. In 2015, when I was in Sydney for the World Hydrogen Convention, I was in the main auditorium at the exhibition centre up there, and nobody had heard about the Kawasaki Industries project, but they used that World Forum to actually present it. And they put their display up, and it was the main guys from Kawasaki, and they put the display up, and they talked about these custom-made bulk tankers that are going to be used to actually take that and use it for stationary power in Japan. And there was a guy, in fact, a colleague of mine knows him. He's a professor at Curtin University in Western Australia, and I suppose you could half call it a heckle what he did, but he stood up and he pleaded with the guys from Kawasaki Industries not to go ahead with this project. He says, come to Western Australia and you can have all the hydrogen you want, but we'll make it with renewables. And so that kind of answers the question. First part of your question, not cheap. Those ones that I showed there, $780,000 each for a 500 kilowatt electrolyzer. But that's a fully self-contained, it's plug and play. You drop it on the ground and just plug it in and off it goes. It's very, very sophisticated technology. Yes.
I'm not as clever as all these guys. I've got a pretty basic question. Something really turned me on in your presentation, and it was those transformers, the voltage dropping transformers. And it interests me. Yes. What interests me about them is what sort of size were they, and do you see that as being scalable to larger and smaller down to even domestic level systems? Where I am, we routinely have between 250 and 253 volts, plus above that, but they don't tell you about it. But the potential savings just in terms of appliance reliability seems to me to be, it's probably worth doing, but what's your take?
Yeah, and obviously, one of the reasons why they're more popular in commercial buildings is because it's bang for buck. You've got a lot of equipment downstream of those things, and so you're likely to get more savings. I don't, I stand corrected here, but I think there is somebody that does a small domestic version, but I don't know anything about it. I wouldn't have thought it would be hugely beneficial in a domestic situation, but it's like I say to a lot of people, when we look at building a new council building, whether it be a $3 million community centre or whether it's a $600,000 just sports change room or something like that, and they say, oh, well, that little one wouldn't need solar, and I said, well, everything needs solar if it uses electricity. It's just a question of what size system you put up. It might be a 1 kilowatt system versus an 80 kilowatt system. And I think it's the same with that. I think, if they were cost effective, they would make a difference because, by reducing that voltage, you're taking the pressure off those appliances, which are losing energy in heat, which is how they work. But we generally only put them on the very big buildings because that's the bang for buck. And the ones you saw in the photo, they were 200 kVA each. So they were quite large. And we've got varying different size ones everywhere else. The interesting thing about that, the one that we have at Brunswick Town Hall, the particular substation area in that Brunswick area is very susceptible to massive rises and falls in voltage. And whenever you put them in, you do some data logging. So you test the voltage for a month, and then you download and get a trend graph to see what it was. And we were getting a strange phenomenon at that particular site that was linked to that local substation, where the voltage was dropping dramatically for half an hour every Thursday afternoon. And then, of course, when we approached City Power about it, they said, no, it wouldn't be happening. No, we wouldn't know anything about that. And so what it meant was that we had to invest more money in a variable servo unit, because even if we only tapped it down 6%, at the time that voltage drop occurred on the grid, we would be below the 220 minimum, which would then affect your building operation and your appliances. And so we had to actually put the servo in. The flip side of that, of course, when you put a servo in, it means that you can maintain on a single phase 221 volts plus or minus 1 volt all the time. And so you're actually getting more bang for buck. So that particular one, we invested more money in it, but that's giving us about 11% return or saving on electricity, because it's maintaining that voltage irrespective. And so you're seeing the voltage come in from the grid like this, and then on Thursday afternoons like this, and then downstream of the unit, it's virtually a straight line. But we had to do it because the only way we could put that technology in there was to put a variable unit in, because if you had a fixed tapping of 3%, it wouldn't give you a return on investment. So, yeah, as I said, there are smaller ones, but I'm not that aware. We generally don't worry about it too much on the smaller buildings because it's all about bang for buck, you know. I solved the problem myself by going off grid, and my inverter set at 230 volts all the time.
You can get auto tap changing regulators from RS components. Yeah, they go down to 200 VA.
Yeah.
Small.
Yeah.
The solid state switch.
Yeah. And put them on individual sub-circuits.
Put them on circuits.
Yeah. Yeah. Mm.
Well, looks like
Just a moment, Chris. We have
have another
female
question.
priority.
Is it just a very, maybe it's a pie in the sky type question, but do you ever see a stage where the gas could actually, you could use solar and gas in a normal household situation? I know the cost would have to come down quite a lot, but do you ever see that being as a possibility?
Sorry, so solar.
Using your own solar to make the hydrogen to run a fuel cell rather than using batteries.
I think, I don't know is the answer to that question, but I think it's possibly, it has very similarities to the question we said before. When you're down such a small scale, I think the laws of diminishing returns would kick in, because you have to invest a certain amount of money in the technology, and if it's only very small, it would be harder to recover the cost. What I can say is one of the other uses that's very popular overseas and is becoming a big thing here, and particularly in South Australia where they're doing some work over there, is injecting hydrogen into the gas network. Now, generally speaking, you can't inject more than 15% weight into the network, but and I don't know the exact figures, but it has a massively larger effect on decarbonising that gas because you put the hydrogen in, because it makes the gas much more efficient downstream. And they're doing it over in Europe. So what they're doing is they're making hydrogen with excess renewables, and they're injecting it into the natural gas network to decarbonise the gas network. You can't use it directly, although having said that, there's a guy in New Zealand that swears by, sausages cooked on a hydrogen barbecue, because all of a sudden you haven't got the hydrocarbons in your meat. And he said, you've never tasted a piece of meat that's just been cooked on a hydrogen barbecue.
Any more questions? Well, I'd like to thank you, Stuart, for a great talk.
Pleasure.
And very interesting. We do have to be out of here by 9 o'clock, so you're welcome to stay and talk. After that, we're going to move over to the Prince Alfred Hotel in the back bar, and if you want to continue talking. So thanks again, Stuart, for a great talk.